here we are only dealing with positive integers, but here we are only dealing with both negative and positive integers. Okay? Here we are dealing with decimal numbers, and we have some integer, comma, some other numbers. The decimal, we have some rational numbers, and yeah. So we will be understanding what is integer, what is decimal, rational, real. So given a number, you need to answer the question: which type of which class this number belongs to? Yeah, which class this number belongs to? So if I give an example, 1.5 now, I ask you, is it an integer or rational, or at the end of this first chapter, not this module, but this first chapter, you need to know, this belongs to real numbers, rational, and so on. Okay? And we will also learn how to correlate numbers, because we be doing some calculation. If I give an example, I want to do 2 plus 3, okay, multiply by 5. So those are numbers, right? But we have different operations. We have addition and multiplication. So how to do this operation? Which type of law are we going to use in order to do this kind of operation? So we will be seeing that there are some law called associativity, commutativity, distributivity. That's what we'll be learning, right? So that's the basic thing. Okay. So if I say something you don't understand, just stop me anytime. So what is a number? If I ask you, can you define number? What will you do? What's a number? What's the definition of number? Unit of measurement. Okay. Yeah. This one was that way. Numbers. So you said units, but units. What's the goal of unit? Is to quantify. To quantify something, right? Quantify, give the quantity of something. And whenever you talk about quantity, you talk about how much and how many. How much and how many. So if they ask you how much and how many, the answer should be numbers. Because you cannot answer this question without numbers. Right? So it's a unit to quantify and answers the question how much and how many. Okay? And if you say numbers without no precision, you should know that we are talking about real numbers, because yeah, the common sense is real. We are all dealing with real numbers. But when we go a bit further, we go into the complex numbers that we use the imaginary method. That will not be too much of our focus throughout the course. Okay. So when I say numbers, without any precision, we should understand that we are talking about real numbers. Okay. And there is a relation between all those relations. So we have an inclusion. So when I do this symbol means an inclusion symbol. That means that this is a subset. You know what's a subset? Do you know what's a subset? A subset. Okay. Subset. Yeah. Okay. If I take the city of Port Elizabeth, we have different regions called Somerstrand and the Sandbar City. So Somerstrand is a subset of Port Elizabeth. Is one part. So you have if you take the integers, say the natural number are somewhere here. That's what we call subset. So this symbol means that this is a subset of integers, and the integer is a subset of this one numbers, and this one number is a subset of rational. Rational is a subset of real number, and real number is a subset of complex number. So by transitivity, if I say that you are less engaged than her, okay, when it's you are less engaged than her, you are less engaged than her, and you are less engaged than her, that means that she is less engaged than you, right? So it's the same thing. By transitivity, if this is a subset of Z, that means that the positive integer is a subset of real numbers. So when you say a positive integer, you are talking about real numbers. Positive integer is a real number. If you take a decimal numbers, it's a subset of rational, and it's a subset for real numbers. So anytime that you are dealing with a decimal number, you should know that it's already a real number. Okay? Any question? Any question? Question so far? It's fine, yeah? Okay, so we have some type of numeration. Eh? So when I write n here, it connotes integers, positive natural integer or positive integers. Okay? And it starts with 1, 2, 3, up to, okay, infinity. So that is a counting process. 1, 2, not 1.2. 1, 2, 3, 4, 5, 6, 7, 8, 2. What you can count with your finger. Right? It's a positive integers, also called yeah. Okay? And when I write n and I put the 0 here, I include 0 inside. So instead of starting counting from 1, now I start counting from 0. Yeah, so we have start from 0, 0, 1, 2, and so on. Okay? And this is called whole integer, So whole integer is just that we take the positive integer and we just add 0 to it. That's all. Okay? So if I say integers and I did not present whether it is natural or whole, you should know that it is just integers. So this set, we call it integers. Okay? So integers could be positive or negative. Example, this set is equal to, you have other number minus 4, minus 3, minus 1, 0, 1, 2, 3. You see? We go from the negative side to the positive side, right? Both positive and negative. And you should notice that there's no decimal number, it's just something, but we have the negative side. That's what's called integers. Okay? So we have here is a positive integers, natural integers, of the whole integers, and then the whole integers are a subset of decimal numbers. Okay? Any questions so far? Any question? Okay. So now let actually look at this class. All that you have seen, they are all class. Natural integers, decimal, rational, rational, real, complex, they are all class. Okay? Class. So what's the meaning of this? Rational numbers. How can we write rational numbers? Those rational, what they look like? So we want to understand how can we quantify these rational numbers. Okay? So every time that you are dealing with a type of numbers, you should know the representation. And the representation. When I see this type of representation, I know that it is real. I see this type of representation, I know that it is a decimal. Okay? And the rational number, they are of the form they are usually at this form. A over B. That's what we call rational numbers, A over B. A over B. They are this form. And as you can see them, they have the numerator and the denominator. Okay? And numerator, denominator, they are both. They can be both integers. Remember, you see the order that we have now. Eh? So if I am here, I'm dealing with rational number. I'm dealing with rational number. I can take any numbers, that could be integer or natural integer, decimal, to be my numerator. Right? Any. And my denominator, I could take any numbers from this interval, from this range, to be my denominator, right? Except that the denominator has to be different of 0. It's a very important fact. The denominator has to be different of 0. The denominator, has to be different of 0. What does it mean? You cannot write 5 over 0, for instance. That doesn't make sense. It is invalid. Mathematics is not correct. You cannot divide a number by 0. If you can, you try with your calculator right now, you see that it will say error, something valid or something. So that means that rational numbers is of this form, a over b, where a, b are what? To be integers, like we say, where a is, okay, when I put this symbol, are you familiar with this symbol? Element, are you more familiar? Element of z, b, element of z, okay? But if I put star, you know what it means? If I put star, you know what does it mean? Huh? Star, it means that I remove 0. I remove 0 from the set of integers. Okay? I remove 0 from the set of integers. So that means that simply this denominator should be different from 0. Okay? So when we talk about rational numbers, you would actually classify them. A rational number could be either integers or either square root, either repeated decimal or either terminal decimal. Let me write down. So these rational numbers, I could write them, is either integers or square root. Repeating decimal. Terminal decimal. Okay? So it's in either the form. Okay? Either integers, square roots, repeating decimal, terminal decimal. What do I mean? If I take 1 or 2, 3 is a rational number. Why is the rational numbers? If I ask you why 2 is a rational number, how will you answer this? Huh? How will you answer this if I say 2 is a rational number? Why? Because 2 can be written as 2 over 1, where 2 is a numerator and 1 is a denominator. Because see, 2 equal to 2 divided by 1, right? I divide every number by what I found is the same number. So you can see that I managed to write them of this form. So where A here is equal to 2 and B here is equal to 1. Can you see that? So therefore, 2 is a rational numbers. So if I ask you why this or your number that said is a rational number, you need to tell me that it can be written. It can be represented exactly like this, A over B. And you tell me what is A, you tell me what is B. Okay? So either it is integers. So any integer actually is a rational number, right? And any square root is a rational number. You could ask me why any square root is a rational number. square root, if you take the square root of 4 or square root of 9, what do you get? Square root of 9, what do you get? 3. Okay, so 12 if y square root of 9 is 3. 3 is what? Integers. So, and 3 can be written as 3 over, that's all. Okay? Here. Alright. So, and we also have the form repeating decimal. So you will get, whenever you are doing some calculation, you could get some time that when you do something, you get 2.15151515. Do you see that? It's a decimal. Whenever you get an integer dot something to something, is a decimal number. So a decimal number, the representation of a decimal number, you get, let me write, d dot, d is a natural number, okay? Dot, you see the dot there, dot some numbers, okay? So an integer is a decimal number. If I ask you why integer is a decimal number, what will you answer? Why integer is a decimal number? Because if I say 2, 2 can be written as 2.0. Yes or no? Huh? Can we write it like this, right? Okay, very decimal. Okay, so so if I have this kind of representation, notice that 1, 5, 1, 5, 1, 5, 1, 5 is repeating. So we call it repeating decimal, because 15 is repeating. It could be infinite sequence, but it is repeating. Okay, it's repeating. So it's called repeating decimal. But sometimes you get some sequence that can never end. 1, 5, 1, 5, 1, 5. Because your calculator here have finite numbers. You see the screen here has a finite. So you can never know that actually this sequence is infinite because it will just give you at a certain limit. So when you are doing some calculation, with your calculator, you will not be able to know that this is an infinite decimal numbers because the calculator will just limit according to the memory. So that's but you still have some repeating decimal that are infinite, and then you have a terminal decimal. The terminal decimal that means that for example, if I do 3 point, this is terminal. This is terminal. And there is no repeating sequence there. And after the comma, there is no repeating sequence there. Okay? There is no repeating. So a decimal number is either you see either that the sequence is repeating or the sequence is not repeating. You can just observe. Do you know the value pi? You celebrate the Pi Day. In mathematical community, we celebrate Pi Day. Okay, a pi is a number that we call log. That number, if you on the calculator, you see some sequence there, and you will see that there is no repeating sequence. There is no repeating sequence, but it is an infinite. Just that the calculator will just give you some limited. Yeah, that you go. What do you find? 5. Okay, you can try with your calculator. Yeah. So yeah. So one thing that I want to let you know here, you should be able to also do some mental calculation. There are certain ways that we will actually not accept calculator. Okay, just be aware. Okay. Any questions so far? Any question? Yeah.
In negative numbers,
Negative numbers. Negative numbers. You say negative numbers. Which type of number are you dealing with? Remember, when you say negative numbers, automatically I see myself in real numbers. When you say numbers, look out for no break. everything. Okay? So now you're asking negative numbers. Decimal. That's his question. So say negative number is negative number decimal. Okay? Look, if I'm here, if I'm somewhere here, am I a decimal numbers? Logical thinking. If I'm here, am I a decimal number? Huh? Okay, let me do the diagram. Suppose that this here is a rational number, right? This is rational number. I wrote it Q. Huh? And the decimal number is actually inside rational number. Okay? So I will need to get a subset here. A subset here. That is my decimal. Okay? So yeah.
Would you be able to put it in numbers? Because when you're putting the letters, I'm getting kind of confused because I'm not seeing what the picture is trying to
The picture. Okay. Yeah, I'm coming there. Right? So but I want you to see the graphical, overview, right? So you see now that this Q actually is a set that cover all the rational numbers. All the rational numbers. When it's red Q is a set that cover all, is a families. That cover all, right? So here now, we have a family here, okay? And I could start to classify this family. Inside this family, we have, maybe if you say, those who are of the age 9, be this side. Those who are of the age 10, be this side. So we are classified. And if I say those who are of the age 9, they are actually part of the class. So that's exactly what we want to do. So the decimal number here, they are inside. But suppose that if I'm here, am I a decimal number? No, because the decimal number here are just limited by this ball. So I'm not here. So not all rational numbers are actually decimal. That's what you need to know. Not all rational numbers are decimal. Example: the rational number we have rational and irrational. Rational and irrational. Irrational. So if it is not rational, then it is irrational. Right? Okay? So example of irrational numbers, the square root of 2. Square root of 2 is an irrational number. Okay? And why is it an irrational number? Irrational numbers. Why is it an irrational? Because actually square root of 2 cannot be written as this form. So if you want to prove or you want to explain that this is a rational number, you need to be able to make it at this form. But square root of 2, you can never, impossible mathematically to write it as a form A over B. It's impossible. Yeah, it's impossible. Square root of 2, you can calculate it. What you get some, okay? But it's irrational. Okay? Because it cannot be written as A over B. But square root of 9 is a rational number. Because square root of 9 is equal to 3. I think I answered already your question. So when we talk about real numbers, this consists of a set of rational numbers and irrational numbers. When you talk about real numbers, okay? We are almost. So remember the graphic picture of all the class. We know. Remember this graphic picture of all the class. Now, so we are dealing with real numbers. So if I say numbers and I didn't precise, either it is natural or you know that it is real. Okay? Real. So real numbers is either rational numbers or irrational. Does it? It's either rational or irrational. Okay? So, but we know what the rational number look like, and we can try to know what the irrational number look like. So if you know what the rational number look like, and we know the set of all real numbers, in order to know the irrational number, we just take the set of all real number, and then we just subtract. We remove the irrational. So the irrational number is just this set of real number without irrational numbers. Okay? Any question? Yeah. An example. Okay. Example of irrational or rational numbers. No, okay. Here, rational number, you get the square root of 9, square root of 25, right? But irrational number, you get square root of 7, square root of 2, square root of 5, and so on. Because when you calculate square root of 7, square root of 2, square root of 5, this you cannot be able to write them on this form. But here now, square root of 9, you calculate, it gives you a number, and you can write it on the form A over B. Okay? All right. Now, let's try a bit of solving the equation. Are you of this class? What's happened? The class starts at 1, 5 plus 1. We are almost done. Okay? So, all the real number with final decimal expression and final decimal expression are rational numbers and can be converted to, let's look at this property. So I say that all real numbers that are here, they can be numbers with final decimal expansion. Okay? And in final decimal expansion. Final decimal expansion and infinite decimal expansion. You know what I mean? I used that before. Final decimal expansion and infinite decimal expansion. You know what I mean? Okay, if I say 2.567, this is a final decimal expansion. It's final decimal expansion. It's a decimal number, but it's final. Okay? But in final decimal expansion, it can never end. Okay? It can never end. Alright? So real numbers, they are actually either final decimal expansion or infinite decimal expansion. Okay? But they can be written of this form, 10 A over B. Written at this form, A over B. As I put the rational number, they can be written as A over B. I give an example. Let's look at this example. Okay, so when I say all real numbers, all the rational numbers, I say all rational numbers is with finite expansion or infinite expansion. They can be converted on the form A over B. And give an example. Let's take the number x is equal to 0.8. Okay? And 0.8, and I put dots over there. That simply means that 8 is repeating. Whenever I put dots above 8, it means that the 8 is repeating. Okay, so actually, what I wrote this is repeating, 8 is repeating. It's an infinite expansion sequence. Okay? But for me to not write this I could just write it like that 0.8. Okay? So 8 is a decimal number with infinite. Yeah.
Okay. So you said when you were writing it, you write 0.8 and then dots in it. Then you made an example when you said it was 2.5151515. How do you write that down?
Yes, exactly. So 2 point 2.15. Yeah. So that simply means that 1515 is repeated. Okay? Simply means that 15 is and is on a final sequence. It's repeated, but it's on a final sequence. Clear? Okay? So the statement that I made is that a rational number can be and is a decimal number with infinite expansion. Yeah, I say a rational numbers is decimal, finite decimal expansion and infinite decimal expansion. Okay? Okay? Finite decimal expansion and infinite decimal expansion. But in order for us to clearly understand that it is actually a rational number, we need to be able to convert it because we know the representation of rational number. We know that rational number they can all be written as this of A over B, right? That's what we said. So if I ask you, this X a rational numbers? That's the question. Is X a rational numbers? Huh? What will you answer? Is S a rational number? Huh? No. Why do you say no? Why can't you write it like this? Did you try it? Did you try it and you failed? You didn't try it. So now you see the representation. Now you try to see whether you can be able to write it at the form A over B. If you're able to write it at the form A over B, then it's the rational number. So now you see that where the problem lies. So give me the number now. If you want to claim that it is a rational number, you need to convert it. It's a type of conversion. You convert X to A over B at this form. So let's try it and see what it looks like. If you fail, then it's okay. So let's try it. If I multiply X by 10, let's multiply X by 10, both sides. And we try both sides by 10. 10 times X is what? Algebra. 10X. Okay? And I multiply 10 by 0.8. What is it? What's the answer? Huh? 8. Right? Like this. Yes or no? Yes or no?
Yes.
It's clear. I will just multiply both sides by 10. Okay? Now, let's try to subtract. I want to subtract this. Remember, this is a, okay, this is left hand side or right hand side? Left hand side, okay? With the equality we have left hand side and right hand side, okay? So let's try to both subtract the left hand side, which is equal to the right hand side. Huh? Because the equality there. It's equality there. So if you want to, you subtract both, you still have the equality. So now I will do 10x minus x. I just take this number, this value, and I subtract with x, which is equal to what? 8.8 minus 0. You understand what I did? Who did not understand what I did? You understand that we agree with this number, right? X equals to 8. Let's repeat it. And I just multiply by 10, and I get this. You understand this, right? You understand this? Okay? So you see that there's equality there. Equality. So the value that are on the left hand side is over there. And what are the values that are on the right hand side? Right hand side we have this one and we have this one. And the right hand side we have x and 10x. So if you subtract or you add both, you can also put the equality. So actually when you take this minus this is equal to this minus this. That's all. Okay? Or replace this minus this is equal to this minus this. So that's what I did. Okay? It preserves the equality. Alright? So now we have 9x is equal to what? Remember, let me write, with the equality sequence, this is what it's supposed to be. Minus 0.888888. Okay? That's what's supposed to be. What should be the answer? 8. So if I have 9x is equal to 8, if I want to, you already sign. So let me use later. So if I don't forget to sign. If I have 9x is equal to 8, if I want to deduce x, x is what? Eh? What? 8. 8 over 9. Can we say that x is a rational number? Yes or no? Yes or no? Yes. But you said no before. You see now? So actually, this number that was here is a rational number. Why is a rational number? That is the proof now. Do you understand now? If you bring this in the quiz, will you be able to do it? If you bring it in the quiz, yes.
Any number that is
No, not any number. Not any number. Remember, if you say number, you are talking about real. Right? And as I say, real numbers could be rational or irrational. So when it is irrational, it cannot be like that. When it is irrational. For instance, if the square root of 2, it is rational number, it can never be written like this. Okay? So it's not any numbers. But there are certain type of numbers that can always be written like this, which are the decimal numbers. Okay? So you understand this example, eh? And in the slide or maybe in the notes, you will see other example where they can give you this number. Can you justify that this number is a rational number so that you'll be able to do it? You can do it now. You can do it. If you understand this example, you just multiply. So sometimes if it is you just multiply by 100 or you multiply by 10,000 and then just subtract and then deduce. That's all.